Hello community! Let's have a look what happened in AI just last week. Something really nice. And I want this to be for everybody, for beginner, for experts. We have here our large language model. And we have the pre-training, the supervised fine-tuning, the DPO alignment. And then we have a simple query and the model answers. And we have here the llama model, the anthropic models, and our ChatGPT for Omni. And answers are generated in milliseconds in the inference run. But last week we focused on another kind of large language model. And we have here an inference compute or a test time compute. And you know the models. This is the OpenAI O1, the O3, the DeepSeek R1, and the new Gemini 2.0, the thinking models, where we have explicit thinking time that takes 2 to 5 minutes. So we divide now this in a pure training time compute optimization and then a test time compute optimization. And you might ask, why? Why do we need this? Well, it all depends here, of course, on the query. If I have a very specific query, then the model here in the first place, here a llama model, for example, just generate an answer that the model learned. This is it. But if I have a real complex query, now in the second kind of LLM with the inference compute, I can give now the model time to think about my query, learn something new. And yeah, it is not just a RAG system that it retrieves from a database. No, we are going here a next step level. Because what we're going to do, also here now, we have an inference supervised fine-tuning and an inference reinforcement learning happening now in this phase. Because given my specific query, and we are here about reasoning, causal reasoning, logic and everything, we have now the chance here to further learn and fine-tune and align here the model for this particular query. So we have a better performance. And just to show you, just 8 days ago, I had this video here about the test time preference optimization. And you say, hey, this is exactly what we have here on the normal training time optimization. Now we go from DPO to the TPO, the test time preference optimization. And if you want to see how we perform here, the latest in AI research here on reinforcement learning, this is the video for you. So in general, we can say the second type of reasoning LLMs, they have here the goal of advanced reasoning performance, either in mathematics, in logic, in finance, whatever you are looking for. And I showed you here 7 days ago here that I examined here the O3 mini high model by OpenAI, and I was really amazed by the reasoning capabilities. But right the next day, I did this video about how stupid an O1 model is. And I focused here on the R1 because this is open source and we could have a look at the reasoning process. But the same is true for the O1 kind of models. Now, if we try to understand it, is rather easy. If the model tries to find your solution, it tries here different pathways in the reasoning process. But as you can see, this depth here of the reasoning augmentation is rather limited. As it turns out, and this is why I called the video stupid, they were trained here to find a multitude of possible solutions, but they were not trained to go here really for a deep reasoning, spend here really quite a lot amount of time here into not discovering 100 possible solutions, but go in depth with the second solution and find the correct solution. So we had here that inadequate depth of reasoning happening, and this was here the content of the video, and the research team showed us that these O1 models, they are not at their maximum performance. There is something to gain. Well, yeah, OpenAI had the O3 model, what a coincidence. But in this video I showed you, there's a lack of explicit reward here for the depth exploration and the reasoning. So models like O1 are optimized for the final answer correctness, but not for the reasoning efficiency or the path coherence. And this creates here a disconnect. The model knows what to solve, but it does not know how to structure the solution in an optimal way. This was the inside of this video because, as we noticed here in the tests, there's an abandonment of the correct solution real early in the phase because the model simply failed to understand that it is on the correct track. I showed you a solution by the authors of a research paper called TIP, where they simply recalibrate the model reasoning process. Great. And then after R1, next day, I did a video on the new Stanford S1 large language model that is also a reasoning model. And I showed you the plus and the minus of the Stanford model. And we went into the process of creating this. And I showed you here in this very simple situation, visualization here, we have, for example, a data set, a mathematical data set. And now the elegant solution by Stanford University was to use here 59,000 different training examples. And Stanford used Gemini 2.0 thinking here to extract here the correct mathematical reasoning traces for the mathematical solution. And then Stanford said, okay, and now from all of this close to 60,000 solutions, we only take 1,000 because only the best, the most beautiful, the most efficiently solved, the most gorgeous solution. And they showed that even with a data set of 1K size, if the quality is really high, you don't need 60,000 data sets for your training. If you have a high quality, 1,000 is absolutely enough. So they took this 1K data set on mathematical reasoning and simply took here a model here from China, the QN 2.532B Instruct LLM, and supervised fine-tune this Chinese model on this particular data set they extracted with Gemini 2.0 thinking. And then this supervised fine-tune model they call now Stanford 1. Isn't this beautiful? For the time I told you, just took about here the supervised fine-tuning 26 minutes here on 16H100 NVIDIA GPUs. And the beauty was Stanford could utilize here the open source QN 2.5 Instruct. So the training time computer of S1 was beautiful. But Stanford had another idea. Stanford thought, hey, if I want to optimize here the test time compute because I have all these beautiful reasoning paths from Gemini 2.0 thinking, I have here now for the algorithm side also a brand new idea. And Stanford went here with two-step idea. They say, hey, I just count the internal thinking token here of S1. And I define a threshold, 100 token, 500 token, 10,000 token, whatever is adequate. And I have a end of thinking, a token delimiter. And then whenever the system reaches here end of thinking, I tell the system, hey, wherever you are in your reasoning process, tell me now the answer. The final answer is. And this was beautiful because it kept here the LLM from running crazy here for some incorrect solutions. However, when there was a complex solution, there was also that Stanford said, hey, we introduce now the weight token for the model reasoning trace to encourage here more exploration. So you see, beautiful idea, optimize the data and optimize here the algorithm. And now I showed you what is the effect of both systems. Now, we have here in the video, give you a detailed explanation, the QN 2.5. And if you take whatever test here, let's say 26.7%, and then we take the S1 model now with the Google Gemini improved reasoning without here the, if you would like to call it here, this advanced reasoning. And I jump into performance almost 100%. Look, I go from 26% to 50%. And then if I activate this algorithm test time compute optimization, I just go up 6.7 percentage points. If I have an other benchmark, you see, I just go up from 92.6 to 93.0, so 0.4 percentage point if I activate here the test time compute. So I think we can clearly see the quality of the supervised fine-tuning data is here the most important dominant factor. So the quality of the data set was simply amazing with Stanford S1. So you see, 2 videos on this kind of thing. And then I did the next video here, and I showed you limiting or the LLMs at their breaking point. And I looked here at a very specific case. I asked, hey, when do I have to move for my Anthropic model, for my Llama models, for my ChatGPT 4 Omni? When do I have to move to these reasoning models that are maybe more expensive? Or in the case of R1 open source, which is beautiful. So when to move, or, and I also explored this in the next video, when should I just increase here the model size? So go from a Llama 8B to a Llama 405B. Is there a limit in the intelligence? Is there a limit here in the performance that I can achieve? Well, what if I let a Llama model run for the same task 50 times and then I just have a majority voting? Can I come close to OpenAI O1? And this was the content of my next video, and we looked here in detail here to answer all of this question. And since this is just a weekly update, just want to tell you, we had the beautiful idea to have two new complexity measures. And one, we went here with the combinatorial search space that is theoretically available, and we looked here at the search space size. Plus, and this was the real beauty, the authors of this study showed us that there's a simple Zebra logic, and if we have here the set 3 conflict count, that this captures beautifully the logical difficulty for particular complex problem complexities. So we had here two, if you want, metrics for the complexity of the task of my query, and then we had all the tools that we need to evaluate the performance. And I told you, do not make this mistake if you see here an overall performance indicator. Because look, here we have here in the first part, we have all our reasoning LLMs, no? The O1, the R1, the O1 mini, and they have here great overall performance. But this is here an average. And then you have your Claude Sonnet 3.5, your Llama 3.1, 405 billion, your GPT-4 Omni, and so on. And I told you, don't look at this. Look at the complexity of the task. And we went here for a small complexity where we only had a logical grid of 2 times 2 or 3 times 3. And I showed you, look, here the classical LLMs, they perform not so bad compared. But the moment you move from a 2.2 complexity to a 3.4 complexity, those non-reasoning models, they fall apart. They simply break. They are not able to do a logical reasoning anymore. Of course not. But our reasoning LLMs, our O1, our R1, our O3, they keep the performance. And I explained in the video why. The other question that we answered is, hey, if I just scale up my non-reasoning model, look, this here is a Llama 3.2, this is a 3 billion, this is an 8 billion, this is a 70 billion, and this is a 405 billion. Yes, if we take one complexity metric, one complexity indicator, like the search space size, let's say here at this particular, we have here from the 3B and the 8B a performance accuracy of 0. Maybe we have here 10% accuracy from the 70B, and the 405B is somewhere a little bit at 21% accuracy. So for a certain small search space, yes, it makes sense that you upgrade here from a 3B, 8B, 70B to a 400B. But look, this is converging to 0 performance real fast if you have more complex tasks. And we looked here at the scaling chain of thought tokens that are happening here in the hidden reasoning process, and we discovered the non-reasoning models, they have no chance at all. Because now if we look at the second complexity metric of the set 3 conflicts that I explained in my video in detail, you saw, look, this is the performance, this is close to 0% immediately. And then we had a look here at the O1 mini, the O1 preview, the R1 in orange, and then the O1 here in blue. And the O3 mini high would be real similar here to the O1 performance. So we understood here, okay, this is it if we scale up here the reasoning tokens for the complexity. So we understand when to switch and ship here and move over to the reasoning LLMs. But if we look at this, you understand that this is just a language model. And some people call this the plain large language model, and some people call this the reasoning LLM, or I have seen here an inference LLM, whatever you like to call it. It is just an LLM. But you know, if we add now here a memory, a function calling, we can build an agent. And we can build an agent here from a simple LLM, and we can build an agent from a reasoning LLM. And you can call this agent maybe a reasoning agent, but I just call it an agent. And in my next video, the next day, we went now and we jumped from an LLM performance to the agent performance. And in this video about QNet, we had a simple goal in the video. We wanted to build more intelligent AI agents that are able to solve more complex interactive tasks. So this means if this agent goes on the internet with your credit card shopping for you, you wanted the interactivity here wherever the agent will go in the internet, that this is performing and doing a great job. And we looked here in particular at the optimization of a process reward model in inference. So we had here this new idea of QLASS, or a quality-guided language agent stepwise search implementation. And we found this is perfect to increase the performance in complex interactive tasks, like you go shopping or you do some deep research with this. And we had a look at this, and I give you this visualization in my video, and I explained exactly what we are doing. And we found out that there is a benefit, because normally in our reinforcement learning, in our reward function, especially in our quality values, normally the system would run here through the complete until it generates a final answer, and then we have a final reward signal at the end of the thinking process. And this, I told you, hey, it's like your final exam at the end of a semester. No, you don't really know what you learned during all these months. And we found out here in this video that with the help of a Monte Carlo tree search, we could build some trees, and those trees would be really helpful if we do not rely on a final reward signal, but early on we calculate the reward much more earlier. And here I showed you that the Stanford model, the S1 model, the reasoning model, had a very simple idea, because what it did, in fact, was just to say at certain times, hey, stop, now tell me the result, and you could then argue, hey, maybe I already reached here the right result. Or maybe here everything is in red, and if I have everything in red, 7 steps in red, maybe there's a lower chance that suddenly, out of the blue, I will find a correct solution. So we looked at this, I explained this to you in detail, and then here from this QNet idea I told you, we now combine something beautiful. So we build our trees with the Monte Carlo tree search algorithm, but we also have now a process reward model. And the beauty of this process reward model is that now at each step we have an estimated reward function. So we have a Q value, a Q score, that tells here exactly the agent, hey, of your 3 options, I calculated here your future reward, your future discounted reward, given my own training process. And I would recommend you click here on this link in the web page if you want, for example, to purchase something here on the internet and you send off your AI agent to perform here this buy. Now, we went in detail into the Bellman equation here as a tool that is still here the sparse outcome rewards into another class that we needed a dense stepwise quality value. And this opened up here the gate here for the QNet. And I showed you how we can train the QNet. This is simply a neural network that learns to predict these distilled quality values. And this is what pushed us further to a better performance. So we did this during the inference time search. And QNet, our little companion to the agent, combined now guidance for the action selection by the AI agent at each single step during the inference process. So you see, we had an agent and we had a quality network, also a transformer network, that was providing here guidance to our agent. So if you want, we had two agents working on the same topic. And wasn't this beautiful? And then in my next video, I want to go into the real world AI product. And I said, okay, so if we have now the perfect AI agent, quotation mark, let's have a look of the performance of a perfect AI agent. And let's use here science as the sector that we examine this. And in my next video, I showed you here a product demo on the homepage from OpenAI where they introduce you to the scientific deep research agent. And I just looked at their product demo by OpenAI and I went in detail into whatever went wrong with this agentic implementation here. And I told you there's a beautiful side also, because right the next day, here Hugging Face decided to rebuild this deep researcher agent as an open source by the open source community. And if you want, you have there the link also to the GitHub, and you can see that this is almost ready and finished right now as we speak. And they here also showed here to implement here an optimized process reward model. So we don't have to wait for the final reward signal, but we can do this at each action that the agent is performing now on the internet, in the wild, performing the action that you want. So my next video, I said, okay, great. So we have now here one AI agent that simply fails on the given task because the complexity is too high for this single agent by this product here by OpenAI. And then I ask you, hey, so what we do now? What is the next logical step? Should we increase the complexity? Maybe not such a good idea, no? Or should we go for a pure AI automation? Should we just let the system run, I don't know, like crazy? Should we go for a deep research agent, pass at 32? So we let the deep research agent do the same task 32 times, and then we just have a majority vote by another agent that says, hey, this looks like this is the best result here by this particular agent. So we would have to pay 33 times here for the deep researcher agent. And then we had a beautiful idea. We went from a single agent to a multi-agent solution. And we said for the next video, let's go one step further. Let's build not just agents, but specialized agents for specific tasks. And then we have a beautiful task, because then we have multiple options to configure our multi-agent system with our specialized agents. So whatever is the input-output of one agent to the next agent, we have options how to configure here multi-agent system, given we have here, specialized agents. Sorry, typics. And this was then the task for my next video. And we went here and we went with an automatization technology that you know here, DSPy here, and we went to extend it to a topology DSPy. So we went from a single agent to a multi-agent configuration system, and we applied the normal DSPy, the topology DSPy, and then I showed you that we can see this here as a pure mathematical optimization problem. And I told you, yes, we had a video months ago where I showed you here with ADAS, there was this beautiful publication that AI agent can design themselves. But given that we have multi-AI agents for real complex reasoning tasks, we needed a more advanced mathematical optimization theorem. And I told you here in this video about topology DSPy prompting the swarm with multi-agents. I said, imagine if we could define the complete complexity of a system in a pure mathematical optimization problem, and I explained why this is the solution to this. So what we ended up with was with a three-part process. We found out, details in the video, that the prompt optimization was essential as a first step. Then the second step was a multi-agent design, a topology optimizer of all the different specialized agents that we developed. And then the third step was, with an optimized topology configuration, again do a prompt optimization. And I showed you for different tasks, we were able to find with DSPy and Topology DSPy here the perfect multi-agent topology to solve those benchmark tasks. And you see here for this particular task of mathematical reasoning, we found out that this particular configuration here with aggregate, reflect, and debate agent with a particular number of iteration, they performed here their best. We came to the conclusion in the video, and I explained it over there, that the performance variation across different topologies of our specialized agent underscore the importance of the topology selection. We have to build our multi-agent framework in particular ways. You just cannot put multiple agents together and saying, yeah, it doesn't matter how we build them. It is really important that you build it in the optimal way. So, influential topologies, and we examined this a little bit detail, but what I finished and what I think was really important to show you that the first stop of the optimization with the prompt had the most significant effect to the overall system performance. And there we are. This is now here the last video from yesterday. And I hope I've showed you why I build my videos, how I select my topics for my videos. And I think, yep, it was a beautiful week. So I tried to give you here an umbrella view, an overview of the complexity. If you don't follow here in detail here my single videos, never mind. With this video, I just wanted to give you here the 10,000 mile view that you understand what is going on in AI in the last days, in the last week, what you should be aware of, where's AI research heading for, what are the problems we are absolutely not able to solve yet, and where we find solutions that are just beautiful to explore. If you like this kind of video, hey, why not subscribe? And maybe next week, yeah, we'll do another AI Just Happened.